Chad Schmidtke. I'm the Director of MapleSim Development, and I want to quickly go over some of the things that we've done in MapleSim 2015.2. As well, after I get through that, I'm going to pass the control of the presentation over to Paul Goosens, my colleague here, and he's going to talk a little bit more about the motivation for some of the pieces that we've put into 2015.2. So before going into any details, I want to step back and just take a look at the Maple toolchain to perhaps give some context for the 2015.2 release. So very often we will have when we think about our products, we've got modeling and simulation. And that's sort of your bread and butter. That's the piece where you grab a model, you construct it, and you get your plots. And so you can start to take a look and get a feel for the dynamic response of your system. Well, of course, MapleSim sits on top of Maple, and that's really the piece that we start to look at for analysis. MapleSim, you can extract your model, you can extract the equations from it. Those equations are manipulatable objects. Maple has over 5,000 functions that you can, in both numeric and symbolic, that you can apply to these equations. And that's where you can really dig in and do some of the analysis on your model and system. And of course, as nice as we say things are about our tools, they're not an island. And so the ability to pull in information from other places and export our models into other tools is also critical to us. And we spend a lot of time, particularly on the deployment side. You can now deploy MapleSim models to the web. We've got a MapleSim server that allows you to essentially interact with them through a browser. We have, as always, the simulation, or the link to Simulink allows you to create S functions directly of our code with extremely fast code that there's no callbacks into Maple, so no license requirements on it. There's also a growing standard FMI, functional mockup interface, that we've been supporting, and this is a growing standard between different tools, and it essentially functions the same way as that Simulink connector, except that it's an open standard, and more tools are adopting it to allow you to transfer models between tools. So if a model's particularly excelling in one thing, you can bring the model there and use that for your analysis. So let's move into 2015.2. So here's the summary. Essentially, we focused on the modeling and simulation piece for 2015.2. So if you recall that previous slide there, we're squarely in the modeling and simulation, although you could think some of the stuff with CAD is integration, bringing things in as well. So and the way that we broke it up is essentially the one was better tools for diagnosing and debugging. MapleSim has physical models. Those can be difficult sometimes to track down where your errors are or what things you need to change. And the other piece is allowing you to make use, basically building models faster. If your company has CAD and they have CAD models that you've created and used, you can now bring them into MapleSim very easily and use and start to do a dynamic analysis upon them. So let's look at that first point initially. This is really the MapleSim engine work. The first thing is a failure information. Now, if ever you get, if you use a causal modeling tool or a physical modeling tool, you'll know that sometimes the errors you get can be somewhat cryptic. Things like index 1 failure, or system is inconsistent, or system singular. And it's sometimes hard to track down where that is. We've made modifications in 2015.2 that now tracks the variables that you use at the top level all the way down through the engine to the actual C code, so that when you select Solver Diagnostics in the advanced settings, you'll get updated information. So the first thing you'll get is if you do have an error during the simulation, it'll tell you the last step, or the variable involved in causing the integrator to fail, that the integrator could not meet the error tolerances for. So that gives you an idea of where to start looking. It doesn't say this is your problem, but in this case, you know, likely main pump 3 omega, there's something going wrong. The integrator can't meet the integrator can't meet the tolerances on it. That's a place to start looking. It will also tell you the last event that fired in your system, which means that you may have switched. Events are often a thing in physical models that switch from one configuration to another. And sometimes the real culprit is the last event. It's put you in a poor configuration, and that's why your system fails. Again, it doesn't tell you exactly what the error is, but it tells you where to start looking. We've also added summary information so that once you start running a model, and your model goes to completion, perhaps it takes longer than you would have liked, or you'd like to optimize it in some way, it gives you a summary of, for instance, the variables involved in shrinking the integrator step the most. Why is that important? Well, that's usually the case. It identifies the variables the integrator struggled most with, which might give you a clue as to where there's some robustness issues with your model. It also gave you an integration, the event summary. So if you've got some chatter in your system where certain events are bouncing back and forth, you'll be able to identify that, and hopefully it'll give you a clue of how to solve any issues that might come up or make your model more robust. A last piece I want to mention is the inconsistency information. Inconsistent system equations can be created using physical models, and you can't tell by looking at that resistor network on the side, resistor capacitor network, that it's inconsistent. However, if you run the simulation, in previous versions you would have been told this is an inconsistent system. Now it'll give you specific equations that lead to the inconsistency. Again, a place to start debugging your model. So that's the diagnostics piece. I wanted to also look at the CAD piece. Now I'm only going to just briefly go into this because Paul's going to take some time sort of explaining it in more detail. So the CAD Toolbox, in a nutshell, is the ability to pull in CAD information from any CAD tool and bring it into MapleSim. But let me pass it over to Paul, and he can tell you more about it.
Yeah. Thanks a lot, Chad. So what I want to do is just set the scene in terms of some of the motivation behind the development of the CAD Toolbox, and really just give you an introduction of how we envisage the CAD Toolbox going to be used in the design environment, and then we'll go through a detailed demonstration with Chad. So part of the motivation is the fact that we've been getting a lot of inquiries and a lot of manufacturing and equipment manufacturers and machine design groups coming to us to help them to produce functional validations of their design, basically virtual prototypes of their systems. And largely this is driven by the fact that they are starting to hit certain problems when dealing with dynamic loads and trying to get an understanding of how those transient loads can actually overload their components. Also the ability to be able to determine what the actuator motions for various end effector motions should be, given that there are certain displacement, speed and acceleration constraints that are required. And then probably, and again, these are just high-level issues that our customers are hitting. Undesired vibrations, instabilities, or thermal problems that are causing issues that only come up when they start building the first prototype, or even when they get the final product out into the field. So the reason why this is happening is because they're dealing with complex systems. They have multiple subsystems, they have multiple domains, engineering domains, different groups that are focusing on those things, and typically they have disparate tools that focus on each of those domains. And it's only when you start putting these things together that it becomes very important to understand what the interactions are between one subsystem and another. You can make a very innocent change in one subsystem, and that can have a very detrimental effect on the rest of the system. Consequently, it's when you start integrating these things, putting these subsystems together, you start to get the real costs in terms of the design and prototyping. So if you can create some kind of virtual prototype or some kind of system level multi-domain model, you can get a lot more insight into the overall behavior of the system, and that's really why people are coming to us in order to perform modeling and simulation or virtual prototype to get an understanding of the dynamic behavior of the overall system and so forth. But it goes way beyond that. Once you've got that understanding, once you've got access to that virtual prototype, to be able to get access to the parameters or the underlying equations and start doing some investigations of the parameters in terms of design space exploration, doing what-if analysis right through to very rigorous optimization. And then finally be able to integrate that work within the workflow, within the existing workflow. So be able to take the work that you've done and then integrate it into the rest of your tool chain. And also, the way we have done this is through the use of MapleSim and Maple and the availability of the connector, MapleSim server. So that it helps on the deployment side of things. But But what about the actual integration with CAD? And this is what we've been working on, and we've been releasing with 2015.2 with the MapleSim CAD Toolbox. So now we can actually take the information from existing work that's been done in the design and use that to create the virtual prototypes within MapleSim. At a very high level, and Chad will go through this in a lot more detail, but what we're offering is painless CAD model import, very easy to bring in models from the standard tools, CAD tools, as well as some of the cross-platform formats like Parasolid and Step. We provide an environment for easy preparation of the model to actually get it to a point where we can actually create the multi-body model within MapleSim. And then from that to be able to create the virtual prototype by combining the mechanical system with the electrical system and so forth. So combining all the various subsystems together, so in this case electric motors, batteries, thermal systems and so forth, to get a much better understanding of how the system is going to work, or is it going to comply with the requirements for this design, and indeed can we actually do further optimization to make it work better. But because we go way beyond that, once we've got that model in, we can start using Maple as part of the integrated environment to start creating tools for doing dynamic load analysis, parametric sweeps, vibration analysis, inverse kinematics dynamics, and specific tools for things like actuator sizing that can be used to determine what kind of motor, for example, you need to order from your supplier that will actually not only comply with the steady state requirements but also the dynamic states. Give you a specific example. This is a fairly complex mechanism machine which is not working. Okay. So imagine this thing's moving and there's lots of subsystems and mechanisms that are interacting with each other, but the critical issue here is that you want to be able to understand what the electrical loads or the mechanical loads are going to be on the motor, and in order to be able to get a better sense of what size motor should be used. But we can also take it. We can actually probe into the various links within the mechanisms to get an understanding of what the local torques, load torques are going to be, or what the accelerations are going to be, so you can make sure that those motions or those joints aren't going to be overloaded in operation.
Thanks, Paul. All right, so let's take a quick look. I'm just going to do a quick overview of what it looks like to import a CAD model into MapleSim. There's a variety of other webinars going on today that go into far more details on this, but I'm going to just quickly show you what it looks like and give you an idea, I think, for how the process works and how easy it can be. So if you've got the CAD Toolbox installed, you'll see an Import CAD option here on the side, and I'm pointing at a mechanism over here. It's a step file, all kinds of different versions, as Paul mentioned, can be loaded. I'm just going to change the orientation here. It comes in the orientation it was in the CAD Toolbox. So here's my mechanism that I'm wanting to look at. Actually, I'm going to put it this way so you can see the pulley there as well. What you see on the left here is the actual tree structure that you would have had in the CAD tool itself. Now this tree can be modified and regrouped. In a way, this provides you an interface between MapleSim and the CAD tool, and it will remember those changes. So if you re-import that model, if you've made the grouping slightly different, it will remember the new groupings. Why do you want to be able to modify groupings? Well, as you can see here, we've got these sub-assemblies at the top level, and just to give you some idea, when I hit import over here, the conrod, the crank, the frame, and the slider, the top level components and sub-assemblies, are going to become the things that become components in MapleSim. So all of the pieces underneath are going to be welded together to create sort of the single rigid body frame. And you might want to remove some of the small pins and things like that you don't care about for your model, or you might just want to weld them in together, so you group them as such. So that's why we allow this sort of intermediate piece in the import side. You'll notice here that I've only got the bodies or components. I don't have any coordinates that I can attach to. And obviously when I bring this into MapleSim to do a dynamic simulation, I'm going to want to put up constraints, so revolute joints and things like that between the actual bodies. To do that I need to place some coordinates. Now, if, for instance, if this had been a SolidWorks file and I had SolidWorks on this machine, we would actually be able to pull in the coordinates that the mates were between in the SolidWorks file. But if I'm pulling from a step, or if I'm pulling just from a file and I don't have a CAD tool on my machine, I can still get the kinetic information, the bodies and things like that, but I just don't get the coordinate pieces. So one other feature of the CAD Toolbox is that it gives you the ability to provide feature detection. And that's this button up here. And the reason that's useful is rather than trying to figure out, oh, where's the center, what is the axis of rotation, I'm going to select here. You can see it can highlight the center of that circle, and it's added a coordinate now, and that coordinate's z-axis is along the rotation axis of that pulley. And you can see the coordinate I just added. If I go to the shaft here, I'm a big believer in simplified names when I'm doing a demonstration, so I'm just going to truncate that to A. And because, of course, I'm going to be, this is on the shaft of the crank, I need to add that to base as well. So I'm just going to paste that coordinate there as well. It's an identical coordinate, but it means that when I generate these components, the base is going to have a coordinate that attaches, and I'm going to have a nice rotation with no offsets. I'm going to need to do the same thing over here for the sliding body. So I've added a coordinate over there to the slider. I'm going to call that, you can maybe guess my naming convention here, I'm going to call that B. And I'll copy that over to the base as well, because of course it's got to rotate on the base. So now I've added two coordinates there. The next coordinate I'm going to add is the coordinate that defines this axis, the sliding axis that goes through the sliding block. So I'm just going to pick it off at the top there. I've got my coordinate set. That's on the con rod. Call that C. Copy that. And again, this time I'm going to copy that onto the slider because I need to have a place to attach to on the slider. Now there's one more connection I need to make, and well, actually you can't see it here. Let me just quickly grab these guys. Visibility, translucent. Now you can see through. The last connection I want to make is on that back component there, between this connecting rod and the pulley system. But I'm going to do that from MapleSim so I can show you a different way of interacting with the CAD Toolbox. And before I forget, I should add to the frame, doesn't matter where I add this coordinate, I'll just add it on the side there. One more, and this is ground. If I don't add this, I have nowhere to attach it to, the inertial frame, and when I start the simulation, the whole thing, although connected internally, will just drop off the screen. So I need to make sure I add a ground coordinate. Alright, once I'm done moving things around and I like the orientation that I see in front of me, I can simply check this box, accept and return, and MapleSim will go off and it'll import all of those components into the main interface. So you can see the four components. This is a group mechanism that basically just has them all together if you want to drag them out and just take a look. But basically the four components exist here, and I'm just going to pull up our 3D window, our construct window, and I'll just minimize it to the side here a little bit. I hope it's showing up correctly for you guys. And I'm going to drag something on. I'm going to drag the base frame in. Oh, and this time I'm going to add the anchor here and zoom in. And you can see that as I add things, they're going to be appearing here in the bottom right hand corner just to help me keep track of what it is that I'm building. So if I now grab that slider, which we know attaches to the block, I'm going to put that in here. You can see them appearing. This is because it's grabbing these pieces from the actual locations in the CAD that they were in the CAD model. And then I'll drag in the crank finally as well. And so you can see now the mechanism's there as it was in the previous window that was actually showing the CAD model itself. Let me just go to these subsystems and show port labels so you can see the ports that we created in the CAD Toolbox. And you can see we're still missing the connection between this connecting rod and the crank. There's no way to attach them here. I've sort of set the other things up. So I'm going to quickly double click, and this is just a feature detect window, so I can go in and modify this component specifically if I'd like. And I'm going to add a coordinate onto it here. There we go. I'm going to call that D. What I should have done when I grabbed that there, let me just quickly. Okay, Great. And then I'm going to open the crank and just paste that coordinate that I just copied as well and hit OK. So now my coordinates are set up. The rigid bodies and such that is inside of these is all set up. You can see the way that I accessed this was just double clicking. Normal when you double click on a subsystem in MapleSim, you just go inside of it and you see the components it's made up of. If it's a CAD toolbox, it opens it actually in the feature detect window that gives you a way to interact with it. You can always go underneath if you need to, open component, and just see the MapleSim components it's transferred or translated that into. So let's start hooking this up. I'm going to go to the multi-body library, the joints, and just start bringing out some joints here that I'm going to use to hook things up. Now, you'll recall this C was if you want to know what axis or what coordinate something is, if you select it here in the 2D space, you can see it highlighting here in the 3D. That's just to give you a sense of where you are. And the blue arrow there indicates it's the Z-axis, so I want this slider to be along the Z-axis. So here I go. I'm going to hook that up. Hook that down to C. Now I'm going to hook up this guy over here. It's the revolute. By default, this is about the Z-axis, so that's perfect for us. Need to drag another revolute out. That up to A. And finally, one more revolute to complete the chain. Now, I need to remember to attach this to ground. As I said, if I don't do that, this is just going to fall when I finally simulate this model. So there you go, I've hooked everything up, and I should, if I've done everything correctly, just be able to run the simulation directly. And it's going to switch over to the simulation results window when it's completed. There we go. And zoom in on it here. And you can see it just swinging back and forth under gravity. So very quickly I was able to sort of bring that CAD model in, hook it up. Now, in fairness, I have done this before with this model, so it's perhaps not always quite that straightforward, but it is a fairly quick process. I'm going to pull a bit of a cooking show maneuver here and dragging another version of that where I've added some additional things, because you want to bring it in for dynamic analysis, but you also want to be able to perhaps add some multi-domain pieces to it. So here I've just added some frictional bearing and added a DC motor to drive the crank. We've got a lithium-ion battery that we've taken care of some of the thermal losses over here, and I've traced the end effector. So now when I simulate this, rather than it just sort of dropping and floating back and forth under gravity, we're going to have some actual actuation coming from sort of these multi-domain components that I was able to add. And now when I do the analysis, I'm just going to shrink this guy here and drag him to this corner. You can kind of see here's the path that end effector is tracing, or the tip of that slider is tracing. You can see how it's moving along. These are the torque draws for the motor, and these spikes are something actually designers often wanted to pay attention to. What is the maximum load that that motor is going to be receiving? And for here you can see sort of the state of charge decreasing in the battery as this thing rotates and it's pulling energy. That's really what I wanted to show about the CAD import. Like I said, there's some other webinars going on today where you can get a few more details on it.
So just to summarize, really, what you've seen today is that MapleSim is a very powerful tool for doing resolving machine dynamics and simulation analysis of mechanical systems by simply being able to import the CAD mechanism and to create your multi-body model, as Chad has shown you, and then be able to incorporate physics models of the gearing, servo motors, hydraulics, any of the actuation systems, to be able to then develop the virtual prototype for doing kinematic and dynamic analysis. So if you want to take a look at peak loads or at transient loads and so forth, this is a very powerful tool for doing that. And of course, Maples itself, as part of the MapleSim environment, you can then perform a wide range of analyses for design space exploration and parameter optimization. And really, this with the introduction of the CAD Toolbox, this really does round off the products that we provide for doing model-driven innovation, or using a model-driven approach to get design insights in your designs, in your products, and fundamentally to be able to reduce project risk, produce better products and get to market faster.